Okay, let's start. Thanks. Hopefully none of you were affected by the fires. And welcome to LA for those of you. It's the first quarter, I guess. This is becoming a annual ritual almost. Okay, so logistically, I'm going to again do office hours right after the class, and also, so I'll stay for an hour or so. If any of you are still waiting for hardware, like I think I still have a couple of eSense lying around, so maybe some groups haven't picked up because I brought in as many as Vikrant had asked. In case you are still awaiting the hardware, come by. So a week ago when we were discussing, so last time I had kind of branched into some of the assumptions that the initial take at real-time scheduling had made. Kind of we were one by one relaxing them, and the one which we spent a fair bit of time was this notion of when resources are shared, and we saw this whole notion of kind of the priority becomes dynamic in part now, and depending upon what resources you are sharing, and so we kind of spent a fair bit of time, and the solution to that was these sealing protocols. And then towards the very end, what I started doing was to look at another kind of another way tasks interact with each other, and that is if one task's output feeds into another task. And that's very common, that one task produces an output or an event which the other task takes. And generally in these systems, what happens is you'll have a cluster of tasks which are kind of running at the same rate, in the sense that every time a task produces one data sample, the other task is run once to process that data sample. Sometimes they are in a ratio, like one task may produce 5 samples, and then that bundle of 5 is processed by the following task as one. So there will be some sort of a clean ratio between how many times one task runs to how many times another task runs. But be what it may, we can abstract all of this. So in the simple case where every task produces one data item and every task consumes one data item, you'll probably have this kind of a graph. Where in this case what happens is, from when something happens from outside the system causes task 1 to run, task 1 produces outputs, an output sample on each one of its output ports, and those in turn cause T2 and T3 to run. Then when T3 runs, then its output goes to T5, and so on and so forth. But the main thing is that we no longer have the liberty of just thinking in terms of priorities and highest priority runs, because if T1 hasn't run, then T2 cannot run until T1 runs and produces an output, for example. So in these kind of settings, so firstly, this kind of a graph is often simply called as precedence graph or sequence graph, the kind of variety of names. Excuse me. So precedence graph or sequence graph. Associated with each one of these tasks would again be some computation time. So that's the execution time out here in the E columns. And then additionally, oftentimes you will basically just have an end-to-end delay. So like it would be from the point input comes in and T1 is able to run, I want the outputs of T5 and T6 to be ready at some point in time. More typically though, you may have deadlines on the individual tasks as well. So our scheduling problem is now kind of a little bit more complicated, that from the point T1 is ready to run, there are kind of a whole bunch of other constraints that occur. So the variety of ways you can approach these problems, and I'm going to kind of, I presented these 2 slides last time, but I'm going to skip them today for the moment, and kind of step back. So if you think about this issue of when should a task run, is a question we cannot answer independent of how much resources we have. So in our case, let's say the only resource is a processor, but more generally it could be sensors or different types of processors or things like that. So how many resources we have? So two processors. But again, it could be a vector of resources depending upon if I have multiple type of resources. Then the next question becomes assignment, which is which processor do I map a task to? And then finally comes the question of scheduling, which is and where do I run? Right. So all these three questions are important. In the case where I'm given a single processor, then of course the answer to assignment is trivial, and that's the only processor I can run on. And then the scheduling, then I just have to figure out kind of the scheduling. So now, if I'm in the case of a single processor, then the scheduling is obviously simple, because what I can do is, going back to my graph, when T1, when the initial input comes, T1 is ready, I run it. After T1 is done, then some other tasks become ready. I pick one of them. It wouldn't really matter which task out of the ready task I choose to run, because in the end, I still have to take the same amount of net computation time. I can never do things in parallel anyway. So one strategy would simply be start with T1 and kind of execute these things, provided I didn't have to worry about intermediate deadlines, right? So in that case, I'll run through and kind of finish all the tasks by some deadline. And if that final deadline is the only one I cared about, that would have sufficed. But if I do have intermediate deadlines, then I need something kind of more sophisticated. And that is what I had presented last time. We kind of discussed it, kind of the idea being that we start backwards. So we basically say, okay, how much time do I have? So the deadline was 28 for the highest deadline. So I kind of start at 28, and T6 goes there. That was the last time. Now, once I'm at this point, then you can say that which were the other tasks which I could have run. So T6 took input from, so at the very end, T6 and T5 were both able to run. Once I run T6, then I have two possibilities. I could run T4 and T5. Again, I pick one and kind of keep moving backwards. So that's kind of the idea here, and then we squish the whole thing backward. It's kind of a heuristic, but let's go deeper into how do we solve these kind of problems. So firstly, the fact that so looking at this more general situation where I may have more resources, more processors, the fact that it matters is kind of a simple example out here. So let's say I'm just looking at some computation, and there are two types of operations, two types of tasks, addition tasks and multiplication tasks. And then the numbers within the nodes correspond to the task number. So I have a addition number 1, addition number 2, multiplication number 2, and so on and so forth. And stands to kind of reason that if I had infinite amount of hardware, then how much time would this set of tasks take? Assume, let's say, each task takes one time unit. So if I say we're allowed to have any amount of hardware, then what would you look at? Okay, what would be the time if I say to run this task? So there are 6 tasks out here with the precedence constraint shown. If I say you have infinite amount of hardware, infinite number of processors, and each task takes 1 unit of time on the processor, then how much time before this thing could be finished? 3, right? Critical path. Just are going to look at that. But if I have fewer hardware, fewer processors, then of course things will change. If I say I have 1 processor, then how much time? 6, right? I still need to do that. And so 1 processor 6, infinite processor 3, but more generally in the middle. So now in this particular case, you kind of with some effort, you can kind of see that if I gave you, also since there are two types of tasks, so let's step back. Since I have two types of operators, so I will need one, if my processor is general purpose, then that is I can do both plus and multiplication, then a single processor 6 units. But if my processors are special purposes, like one can only do task of addition type and the other can only do task of multiplication type, which is kind of the case we're showing out here, then I'll need one of each type and kind of do them in time 3. So there's clearly dependence upon how much resources we have and how much time it would take. And generally, as a designer, often you're in the situation where you're trying to solve these two problems simultaneously. So there are many different variants. Number of processors and the types of processors may be given to you, and then you are optimizing for the latency, kind of or trying to schedule the system. But sometimes also you have to kind of find both together. In a way, so you may be told, okay, you have a latency budget of whatever, let's say 6, and now minimize the number of processors given that you are going to use. So if we are in a situation of unlimited hardware case, then that kind of the simple strategy would be either to use ASAP as soon as possible. So at time step 1, I'm going to execute every task which is ready to run, and then in time step 2, I'm going to do those which are now ready to run, and so forth, and I'll take the critical path amount of time, and the number of processor is going to be decided by the maximum number of processor used in any given time step. I could also work backwards as late as possible, which is what that heuristic a couple of slides ago was doing. I kind of start backward. Now in this particular case, I would need to know the latency budget I have, so I'm going to kind of start from that and go backward. Again, kind of I can come up with how many processors I'm going to need. In this particular case, you can see that ASAP is worse off because it needs five processors which are sort of working there. Now, what if I have limited, this slide just says algorithms for it, so I'm skipping that. What if I have limited hardware? So now you are given certain number of processors and tasked with precedences. Now you have to solve things. So there are in broad terms, there are 3 methods that get used. So kind of lazy approach, which for the size of tasks one is going to face in a typical software system is often enough, is an integer linear program. So these you can say these are optimal methods. What they're doing is they're modeling the scheduling problem in its full glory and then throwing it at an optimizer, let's say from MATLAB or some such package, and then letting it solve it. And if the number of variables in my optimization problem is small enough, then the current tools out there are pretty good at giving us a good solution. While the problem itself of under limited hardware is NP hard problem, so these are difficult problems computationally, but tools for solving integer linear programs and all have become pretty efficient for the kind of problem sizes you may encounter in many cases. Then there are constructive methods. What constructive methods do is they construct from scratch by a schedule. So they'll basically I'm given a number of processors, so limited hardware. I'm now going to decide this task goes to time step number 1, this task goes to time step number 6. They're going to construct a schedule, and at any given point in time, you're going to have a valid schedule. So it's going to construct from scratch a schedule which is valid. It may not be the most efficient. Okay, so in our particular case, for example, it may end up taking more time that was necessary. So even though it's possible that even with those precedence constraints, I might have met the deadline, they may fail. So one broad category of algorithms here is something called list scheduling, which in a way we already saw, but you see it again. And then there are kind of more heuristic driven approaches. There's something called force predicted scheduling, for example. And a third type of scheduling algorithms are what are called as iterative improvement methods. And the idea here is you're going to start with some schedule and you will assign a cost to that schedule. In fact, the schedule may even be wrong. Like, for example, maybe it might violate the precedent constraint, or it might violate the number of processors you have. But it's fine. You are going to improve it using some optimization strategy, gradient descent or something like that, and then improve it until you hit a low cost thing. So again, optimal method where you basically are shoving the problem into general purpose solver, constructive methods, and iterative improvement methods. So let's look at some examples out here. So for constructive methods, kind of there's this general class of heuristics called list scheduling, and it's very simple. It basically says at any given point in time, I'm going to have a candidate list of things I can schedule which have not been scheduled. Okay, so when I start out, none of the tasks are scheduled. And then while this candidate list is not empty, I'm going to pick a task out. Right? So that's a select candidate, and this will have some magic to it because how you select a candidate is going to matter. And then I'm going to schedule that candidate. I'm going to put it into a particular time step. And at any given point in time, if it so happens that I selected a candidate and I'm unable to schedule it because, for example, I'm exceeding the amount of hardware, then I failed. Okay, so these things may fail to find a solution, even though a solution exists, because they may not be picking the candidates in the right order. So, for example, what was the ASAP one doing? ASAP one was basically when it started out, its strategy was basically so it was basically giving a level to each task and then selecting the task whose level was lower. By level, I mean the distance from the origin, right? So if you recall out here, this is so you could say in the selection phase in the ASAP, it's always selecting a task which appears first. And its scheduling strategy was, in case of unlimited hardware, it will just put in time step 1, but otherwise it will first process tasks which are at level 1, then tasks at level 2, and so on and so forth. So the selection strategy in case of ASAP was that, but you can imagine other type of selection strategy. For example, there might be some concept of generally a criticality that I may do so, and I can pick them up. So there's a whole bunch of list scheduling algorithms which basically play around with the candidate selection process based upon some intuition, some heuristic. Other kind of intuitions might be I'm going to pick a task which is very heavy, as in which takes a lot of compute time. Let's get it out of the way first, or other such possibilities might be there. Again, these are heuristics. So if they can always fail to find the right solution. Then let's pick an example of iterative improvement. So the idea in iterative improvement is that at any given point in time, I'm going to have a schedule and a cost. Except if the schedule is a bad one or even an invalid one, the cost would be very high. But then I'm going to wrap around this thing a procedure by which I'm going to always modify this schedule, playing some games in it to improve its cost. So those of you who have done neural networks, it kind of reminds you of would remind you of what you see with stochastic gradient descent in neural networks. You start with a set of parameter values for the neural network, and then you use the gradient descent to kind of optimize it. You find the gradient of your loss function, your cost function, with respect to the parameters, and then you perturb the parameters, and then you repeat this process. So there are many such algorithms that exist which let you modify iteratively a parameterized system. In our case, the parameters really are the schedule. So I'm basically saying the start time of the task, for example, or the assignment of the task. So I'm going to perturb those. So there are a variety of methods which exist. Simulated annealing is a very common one, and what it basically does is it says I can think of my cost function as kind of some sort of an energy landscape. It's exactly like in case of neural networks, right? I have if across the space of all possible schedules, valid and invalid, you can think of them as having some sort of a cost. And when I start out with some, let's say, randomly chosen schedule, then I'm going to be somewhere in this energy landscape, and then I'm going to do a gradient descent, and I'm going to go down. Now, the problem with gradient descent, of course, is that if my starting point is bad, then I may end up with a bad minimum, right? So you need some way of kind of getting things out of getting stuck in a local minimum. Now, in case of neural networks, we don't really kind of do that, right? We basically estimate the gradient and we sort of move down that path. But there are still sort of lots of hyperparameters and all which kind of kick in and affect things. But in simulated annealing, what happens is we do something which is borrowed from Mother Nature. And the idea is we take an analogy with a physical system. So you can think of, so annealing is something which, actually what does annealing mean? Anyone? Probably heard of it in physics, annealing.
So it was something about heating the metals and at some optimum temperature you be able to achieve that.
Yeah. So crystals, right? Crystals have flaws in them. So to make a good crystal, you heat it up. Essentially, you jumble all the atoms or molecules forming the crystalline structure, and then you slowly cool them down so that it settles in a nice, clean, flawless structure. That's called annealing. So we heat up, and when we heat up, the kinetic energy of the atoms and molecules go up. They sort of, since they can move around, so there's a lot more mobility, and then we gradually kind of slowly cool them down. And as we cool them down, they become more, they become back to being more rigid, right? So high energy state to kind of a low energy state. So it's the same analogy out here, except that instead of the crystalline structure, our state space is really the schedule where the operators, where the tasks are in the time steps. Energy is my cost function. The ground state is the optimal state. I really want to bring it down to kind of the least energy state. Rapid quenching refers to when I heat something up and then kind of suddenly pour water on it or something, and it just immediately cools down, but then you may have a bad crystal, okay? And careful annealing is slowly kind of gradually bring it down. So simulated annealing kind of, so the idea is that if I heat the crystal up, the reason those flaws disappear is because those atoms can kind of move around, okay? I'm not simply doing, in the iterative improvement, we are kind of just, kind of the naive way of iterative improvement, I might simply look at like, oh, there is a local problem out here, mess with it, change the operator around and all. Here, by moving, what happens in hot state of a physical system is that everything is fair game, things can move around. So simulated annealing kind of mimics that. So the idea is we start with an initial solution S, and you literally could basically kind of start with random assignment, for example, right? Not even worry about what the precedent constraints are. But the idea is that when you compute the cost, you will penalize heavily violations of precedence constraints and violations of resources. So if I put more tasks in a time step than the number of processors, I'll have a very high penalty for it. In fact, I'll make the penalty infinity. And likewise, if a task is occurring before a task which supplies data to it, then again I'm going to make the penalty infinity. Okay, so cost will become very high. On the other hand, if it's a valid solution, as in it meets the precedence requirement and it meets the number of processors, then I'm going to make the cost equal to the latency because I'm worried about, let's say, minimizing latency. And then the idea is there is a magical parameter called temperature, and initially it's going to be very high. And then what we'll do is we'll iterate through this process where we are going to reduce the temperature over the iterations. So what what we do is we pick a random schedule S prime of the current schedule. So you need to think of that these schedules, all the possible schedules, they kind of represent sort of points in some high dimensional space. And a neighboring schedule might be something, let's say, for example, I change the order of two tasks. Or another, maybe I move a task one step down or one step up in time. So you can think of kind of all the set of schedules that there exist, and then schedules which are nearby. So it's almost like moves in a game, right? I mean, from one chessboard configuration, I can, if given the set of moves I'm allowed, I can only go to certain board positions. So same, and when I make that move, I may suddenly enter into a win-lose kind of a situation. So it's the same concept out here, that we pick a neighboring schedule by making a local move, and then we can compute what is the change in cost. And the idea is that if it's a downhill move, I always accept it. But if it's an uphill move, then I accept it with a certain probability, except that the probability is a function of how much uphill and what the temperature is. So if you kind of look at this term, what it's basically doing is, if the temperature is high, then the probability I can make a large uphill move is higher. If the temperature is, but as the temperature is lowered, the probability I will make a uphill move or large uphill move goes down. And as temperature sort of really goes down, then effectively I become, the thing becomes like a gradient descent only. Okay. There are kind of variants of this basic idea where you even allow wormholing. So the idea is, instead of simply looking at neighbor schedules, once in a while you basically look at faraway schedules also. So like do a dramatic change there. So very commonly used technique.
Is L stand for the number of levers you have given S?
What stands for that?
Is L, when you're running the for loop, it's like I between 1 to L?
L is just some limit. So the idea is, if there is no solution, or even in this case, when do you stop? So think of it the stopping criterion. Okay, I'm going to run it for so many iterations, and during that time, and after that I'm going to stop, and then I'm also going to keep track of the best solution encountered during that time. Okay, so it's just a limit on my iteration.
T here, the temperature in the actual problem stands for like time constraint we have? Or
No, it's exactly temperature. It has nothing to do with our scheduling problem itself. T is a property of the simulated annealing algorithm, and if you notice out here, what we are doing is we are also reducing the temperature. Okay, so
where is that one come from, the reduced temperature?
Huh?
That RT?
Yeah, so R is, think of it like the rate at which I am freezing my system. Okay, some analogy with, again, those of you who have done some neural network course, the learning rates. Okay, you can say, so it's again some hyperparameter of my algorithm. So this algorithm has a hyperparameter for the rate at which I'm reducing the temperature, and another hyperparameter as well, L for sure, after how much time I'm stopping, and another hyperparameter is let's see, the starting temperature, T in it, whatever I'm setting the initial temperature to, right? So these are my three hyperparameters, and you have to kind of play with these things a little bit. There's some general guidances and stuff like that, but this is kind of like a universal optimization thing for nonlinear optimization problems, and very widely used in scheduling type problems where you don't have, but in many other cases also it's a you can apply. It's slow, kind of, you're gradually annealing these things, and also it's probably not the kind of thing where you are going to necessarily use in an online kind of a system. But if you are optimizing, let's say, floor plan of a VLSI chip, or figuring doing kind of those scale of problems, simulated annealing is often used. You just let it run, and it. So anyway, so that's it. This is a class of class of optimization, which is drawing its motivation from an analogy with a physical system. Okay, and in this case, the observation that physical systems use the process of annealing to settle into a low energy state. And likewise, we are using it out here to solve our optimization problem. Okay, so at the end of this, I would hopefully have a good schedule. So back to our energy landscape, basically what's letting us do is, with some probability, I may take an uphill move, and that may cause me to go over, not be stuck out here, that we get out of the local minimum.
So for the neighbor decision, are we only limiting ourselves kind of to the neighbor as one element in either direction?
You get to define it.
Okay.
Right? Whatever, like, think of it like a game. At any point in time, you are allowed to modify your schedule according to a set of rules. You get to define those rules. Of course, think through it, because a little carefully, in the sense that your set of moves should be powerful enough that you can span the whole space. Right.
If your choice of neighbors is too small,
then you are going to be then you are going to be stuck. Right. Exactly. So your set of moves should be powerful enough. It could even include things like, let's add one more resource, let's subtract one more resource if the number of resources is not fixed, for example, or let's add one more time step, or reduce the number of time step, or shift a task. You get to define. So think of it like you're designing a game. Chess was designed with some rules, and therefore it limits the kind of board positions which are possible, right? So same analogy out here. Okay. Had any of you seen simulated annealing ever before? No one? Okay, so it's new to everyone. There exist a variety of optimization strategies which draw physical inspiration, right? I mean, in fact, gradient descent is exactly that, right? I mean, we just move downhill. In this case, we're saying now we can move uphill also once in a while to avoid getting stuck. And then wormholing basically says, takes too much time to get across. Why don't we Star Trek style, kind of move to a different part of the universe? Okay, so we kind of do long jumps. Okay. So that's simulated annealing. In the same vein as this, there is also, I think in my original list, I also had genetic algorithms. Genetic algorithms draw, I don't have any slide on that, but they draw their inspiration from the way populations, evolution happened, the way sort of optimization of life happened, if you may, right? So intuitively, as I'm sure all of you are aware of, what happens is that we start with a population, and then members of the population intermix, and then there are mutations, and then survival of the fittest, which basically says at any given time of the so when we mutate and intermix, we have a larger population, but the ones who survive are the ones who are fitter. In other words, whose cost functions are beneficial to them, but again in a probabilistic sense. Okay, and the whole process kind of repeats. And so essentially, evolution over course of whatever eons have created optimized population of sorts. But of course, the uphill part is mutation, right? That introduces a random perturbation in that process. So again, similar analogy, you can think of it as that there is a different physical system which did this optimization, and genetic algorithms or evolutionary algorithms, as they're often called, mimic them as well. So in fact, in neural networks, genetic algorithms have emerged as something that a lot of people are using for hyperparameter tuning. So anyone knows what hyperparameter tuning stands for? So hyperparameter tuning refers to the fact that anytime we have these algorithms which have these funny knobs, like, right? So in case of neural network, there are things like learning rate or sort of other parameters. What value should I give to them? Okay, so people often do like grid search and stuff like that, but instead of that, genetic algorithms often get used as well. So that's another one. Okay, the third class of method is the optimal methods, right? Where basically what we do is we say, let's model exactly what we want as an optimization problem, and let's assume that I have a way of solving that exact optimization problem. And and then there is a separate community which works on creating efficient ways of solving certain classes of optimization problems. So if any of you have done like ECE 236A or B, you may have seen linear programming or convex programming. So there are classes of optimization problems which are particularly efficient to solve. So it turns out scheduling can be mapped to a class of problem called integer linear program. Now, linear program is actually very efficient to solve. Integer linear program is incredibly hard. Okay, yet the certain special cases as well as kind of small problems can be done pretty nicely. There are lots of solvers around which you can use from Python or from MATLAB or whatever. And the basic idea is I have a matrix of some size n cross n, which is integer valued. So in standard linear program, it's real valued. I have a set of vectors b's and a set of vectors c, and my goal is to minimize c transpose x, which is basically saying I have a cost function. So x is my x is a vector of variables. So I'm minimizing a linear combination of x, subject to the constraint that ax is less than equal to b. By the way, b and c are also all linear, so they're all integer values. Okay, so it's basically saying I have a set of linear constraints where the coefficients are all integers, and x is an integer value. Everything is an integer, and I have to solve that. Standard linear program, everything is real value, and it's polynomial time solvable. So very efficient things exist. The moment we make it integer, it's incredibly hard to solve, but again, good solvers exist, and particularly for small size problems, you can get pretty good results. So it turns out that a lot of problems we encounter, including scheduling, can actually be mapped to an ILP problem. And for modest size problems, you can just use an ILP solver. So what I'm going to show you is that how can we map a scheduling problem with precedence constraints to an ILP. And while I'm just showing you one example, but think of it like a toolbox, a tool that you can use for a variety of purposes. Okay, not just this specific scheduling problem, but a lot of times when you face optimizations thing of some form or the other, you can map it to an ILP and kind of solve it, and you have a quick and dirty way out. The only thing is, it is not necessarily, it's certainly not going to be the fast way of solving it, and because you're not exploiting any special domain knowledge or stuff like that. Okay, you're kind of essentially using a general purpose hammer to solve this problem. So so let's consider kind of a somewhat simplified situation. So again, remember, we have a precedence graph where we are given where we have some latency constraint. Okay, and I'm going to pose the problem as, so I have again tasks with precedence constraint. There's some latency requirement. So k, I need to finish these tasks with dependency constraints in k time unit, and my goal is to minimize the number of processors I'm going to need. You can change the problem differently. You can say, I'm giving you the number of processors, and I want you to optimize the amount of time the schedule will take. Okay, and other ways you can think about it. And right now, again, I'm going to assume that all tasks can run on any processor. So there's only one type of processor, and tasks can therefore run on any processor. Okay. So how do we go around doing it? Okay. So firstly, I'm going to define an integer variable called y0. And y0 is going to represent how many processors my schedule actually needs. Okay, so it's basically the maximum number of processor my schedule uses across all the time steps. Or another way of saying it, in any given time step, number of processors needed should be less than equal to y0, and my goal is going to be minimizing by y0. For each time unit, So let's say I represents the time unit, so I can go from 1 to k. And again, my tasks only take 1 unit time. So again, I've done lots of simplification. So tasks take 1 unit of time, and I have k time units. So for each time unit, let's define another integer variable, xij. And xij is 1 if computation task tj is executed in the ith time step. Right? So remember, my task has to run in some time step. So I'm going to indicate, so xij is what is called as an indicator variable. So xij is 1 if task tj is scheduled to run in time step I. And xij is 0 otherwise. Now, how many processors I'm going to need in time step I? Let's call it yi. That is going to be the summation over all the tasks for time step I. So it's going to be xi1 plus xi2 plus whatever, right? So I sum up the indicator variables for all those tasks for that time step. So that immediately leads to a constraint saying that yi should be less than equal to y0, right? Because I have y0 processors. Okay, so I have taken into account my the fact that I only have y0 processor, except that y0 is a variable, right? So I'm seeking to optimize that. But I'm still missing another constraint. I'm missing the constraint that what constraint am I missing?
What if some of them need to be done before the other ones? Like
Right, precedence, right? I have to somehow capture that if there is an edge from task 5 to 6, then task 5 runs before task 6, right? So am I missing something else also? So we'll see how we can do that as a linear constraint, but I'm missing one more thing here.
The dependencies between them?
No, dependencies is what he's talking about. Is there something else that I'm failing to capture? What are xi's? Xi's say that task j is running in time step I. Okay. Do you think there is some additional requirement on x?
Like how long each of them going to take?
No, each task takes 1 time unit. See, nothing thus far precludes x11 and x21 both being 1, right? I have to make sure there is a uniqueness requirement. A task can only be scheduled in a single time step and at least 1 time step, right? So task has to be scheduled at least 1 and at most 1. So how would you do that? Yeah, the sum of x is going to be equal to 1. Okay, so sum of x1i plus 2i plus k, right? I mean, for task number I across all time steps, the sum should be 1. Okay, so minimize y0 subject to uniqueness requirement, subject to resource constraint, and now the precedence. So let's say task I has to be done before task j. Okay. And remember, I'm already ensuring that the task is scheduled exactly once. So what I can do is I can give these time steps a weight. So I can give step number 1 a weight of k, step number 2 a weight of k minus 1, and so on and so forth. And now I can basically say that the weighted sum for task number I is less than equal to the weighted sum for task number j. Actually, I messed it up. It should be the other way, greater than equal to. So the starting point, if task I has to be done before task j, that means task I has to be. Let me fix it, otherwise it's going to keep bugging me. Okay, I will correct the slide. So this thing, it should be greater than equal to. So again, I weight x1I by k. So let's imagine task I was scheduled in step 1. Then this will get a value of k. And I'm going to make sure it is, apologies again, it should actually be strictly greater than. Okay, so I want to make sure that task I is scheduled before task j. So I need to make sure that x1j is 0. So the way I make sure is that this weighted sum will have exactly one x entry. And I want the weight on the left hand side should be greater than the weight on the right hand side. So this is how I'm going to ensure that if there is an edge from Ti to Tj, namely Ti produces the data which Tj uses, that is going to be met. So every edge in my precedence graph is going to have a constraint of this nature. And I want to add that to my list also. And now if I feed this thing into an ILP solver, you will find them on the web also and all, you are done. So all you have to do is, given your task graph, you are, for every task and every time step, so if I have 100 time steps and 100 tasks, I have 10,000 variables, and I'm going to have and a few more y's, and I kind of create this complicated kind of set of large number of constraints, feed it there, and let it work. Now, one nice thing out here is that our variables are binary. Not only they are integer, they're just 0, 1. And it turns out that these kind of ILP problems where variables are take values 0, 1 only and not arbitrary integers can be solved particularly efficiently. So you can solve these things in like milliseconds, okay, for reasonably large number of things and get very good results. That's a very important point. So I can map scheduling problems of all sort of different types into a general ILP problem and use it as a general hammer to do it. What I like about the ILP approaches is not so much that it's efficient, but rather that it forces you to think about the problem, right? Because in the process of coming up with these constraints, we had to think about all sorts of things that existed. Another thing you can do is you can improve your ILP formulation by eliminating variables to begin with. So the way you can do that, just to give you an example, remember we saw ASAP and ALAP scheduling, right? ASAP told me what's the earliest a task can run, right? And ALAP tells me what's the latest a task can run. So I can just rule out all those X values which lie outside that range for a task. So for example, let's go back to, I don't know, back when. Let's look at this guy. So let's say I'm looking at operator number 4. The earliest 4 can run is in time step 3. And the latest 4 can run is time step 3. So I can eliminate x13, x23, and x43 right up front. So ALAP and ASAP are very quick and dirty things. So I can run ALAP and ASAP. For every operator, every task, I can come up with a band of time steps it can conceivably run in and only do those x's and forget the remaining. So with simple tricks, you can prune the set of variables and essentially reduce the complexity of your optimization problem. So if you bring this additional knowledge to bear, then essentially you're pruning things away, then your solution becomes a lot easier to do. So that's ILP. Just to give you a more concrete example, let's say I give you this precedence graph. C1, so there's 6 computations in it, and they're again going to take 1 time unit each, and I give you 3 time steps, and your goal is to minimize the number of processors that are needed. So first thing we do is we introduce indicator variable for every combination of tasks and time steps. So I have 3 time steps and 6 tasks, so I have 18 indicator variables. Then I create resource variables corresponding to, for each time step, how many processors do I need. So yi is equal to the summation of all indicator variables for that time step. So I'll have 3 such things, y1, y2, y3, indicating how many processors I need in step 1, step 2, and step 3. And y0 is what my optimization objective is. And then I can list, we'll see in the next slide, but basically you can imagine sigma x I j for any given j is equal to 1, yi are less than equal to y0 for all possible value y0, and then I have the dependency constraint. So in this particular case, I think I again kind of messed up. So in this particular case, 1 is before 4. 1 must run before 4. C1 must run before C4. So, and I have 3 time steps. So I'm going to do 3x11 plus 2x21 plus x31 should be greater than the corresponding thing for the 4. And that is capturing this particular edge. And I'm going to have, since I have 1, 2, 3, 4, 5 edges, I'm going to have 5 such constraints in my system. And so with that, then my scheduling problem becomes minimize y0, subject to yi less than equal to y0, all the 5 dependency constraints, and all the 6 execution constraints. And one particular solution you will come up with out here is this, which basically says I need 2 processors in this particular case. And I think intuitively what is happening is that C5 and C6 can run in time step 3, C3 and C4 can run in time step 2, and C1 and C2 can run in time step 1. So 2 processors. So of course this is a toy example, but you can apply these things to kind of more general situations. Okay. Any questions?
Could you go to
Previous slide? This one?
So that +1 is because C4 runs like 1 step later than.
Which one? This one?
Yeah.
Uh-huh.
That +1 at the end, that's because like C4 runs like 1 step after.
Oh,
C1.
let's see. I think the +1 was actually because of the greater than equal to. So I think if I have the greater than, then the +1 is in there.
Oh, okay.
Yeah, my apologies. I'm going to fix it, but basically, yeah, if you do greater than equal to, then the +1.
And then for each of these precedence constraints, you get one
Equation, one inequality per constraint.
So
Yeah.
it's possible to solve this system in multiple ways, right? You might have
Absolutely. So there may be many solutions to this problem. Now, I guess in this particular case, though, I think so firstly, it is clear I cannot do it in a single processor, right? And if I have 2 processors, in this particular case, I think there's only one solution. Okay, so this particular problem, there is a single solution, but generally speaking, there may be multiple solutions. Okay. So how many of you have used an integer linear program solver before? No? Okay. So again, this is kind of a general purpose toolkit. You can find, you may find it useful for a lot of other problems. Anything you can map, and you'd be surprised. I mean, going in, you will say, nah, it's not linear. But if you be a little bit creative and maybe define your variables properly, a lot of problems map to an ILP problem nicely. Okay, a lot of things that we encounter. You wouldn't have thought that scheduling is a linear problem, but it is, right? As I showed you. So yeah, just sort of remember it, you might find it useful for some other purpose some other day. Simulated annealing, genetic algorithm, same way. These are general purpose tools you can apply to a variety of problems. Just something in your arsenal. Okay, the final thing I wanted to cover in this one, and I'm kind of skipping the latter slides in this lecture. We kind of lost Monday's lecture, so I'm going to just skip them. It's important. Is what happens when we have a distributed system. Okay, so thus far, while we did talk about multiple processors here, but they were still kind of logically kind of sitting in the same place. Okay, it's kind of like multiple cores and all. But oftentimes the systems we are designing are spread across multiple, like far away on the internet, right? I mean, I may have an edge device, and I may have the data from that going to the cloud and then coming back to another edge device, multiple sensors talking to each other and meeting in a data center, things like that. So oftentimes we have these data flows which go across large distances or sort of long networks. So what is happening is, in these cases, is if I look at the end-to-end information flow, it's really happening across many processors. So like, let's take something which we use quite frequently, which is a bidirectional telephone call, voice call, right? So I speak, the microphone at my end captures it, it encodes it, compresses it, whatnot, ships it over. So all of that happens in my cell phone, goes to the cellular tower, it routes it, or perhaps go through a few such hops in the network, and then finally reaches your phone, and then the reverse process happens, decode and play out and all, right? And then separately, we know that there is a deadline requirement in these things. That is, that for bidirectional human communication to be effective, usually the guidance is that the end-to-end delay, that is from the point I uttered the sound to the point you heard the sound, it should be around 150 milliseconds or so. If it is more than that, then we will begin to talk past each other. Okay, and there are similar kind of things you encounter in other systems. In a control loop, for the control loop to be stable, the sensor to actuator delay should be within a certain limit. Now the challenge in this case is that my latency requirement of 150 millisecond is spread, is the total latency of my phone and each one of those intermediate things in the network, the switches and whatnot, and including propagation delay, and then the delay in your phone. So one question which arises in this case is the following: how should I divide up this delay? Right? Thus far, the problem we have solved in our scheduling work is solving a problem. Given the delay budget, given my latency requirement, I can solve the scheduling problem. But now we are asking a different question, which is, I have the overall delay requirement. What should be the delay requirement for this stage? And this is where part of it is about some God entity splits it and says, it's your job to meet this one. And there is a lot of horse trading which will go on. I need more delay budget, you need more, right? All those kind of things. But purely from a computational perspective, I mean, the problem we do face is what's the reasonable way of dividing these things? Then there are additional issues which come up also in the systems. We need to schedule things over the internet, over wireless links and all, and so you have to face with propagation delay. So speed of light from California to New York is how much? Anyone? Any guess?
6 seconds.
Huh?
10 to the negative 6 seconds.
No. That's way too. 10 to the minus 6 is a microsecond. In a microsecond, how much can light travel? What's the speed of light? 3 10 to the power 8 meters per second, right? 3 e8. Okay, so per second. So in 1 microsecond, it will only travel 300 meters. We will not even go past E4, I guess. Right? Okay, so it's around 30 millisecond, 20 to 30 millisecond across the coast. Okay, so that amount of delay budget goes away right there if you are doing something costly. What about how much is the delay when you are going through an Ethernet switch? What do you think would be a rough order?
A few seconds.
Huh?
A few seconds.
Oh no, not at all. Few seconds, no way, right? I mean, if it was few seconds, we'll have disaster at hand. So,
Milliseconds or something.
huh?
Tens of milliseconds.
Millisecond, not tenths, millisecond. So, when you go home today, there's a program called traceroute on your computer. Run that to just UCLA, for example. Say traceroute www.ee.ucla.edu. It will show you how the packet reached your destination and what were the delays along the way. Gives you a lot of insight into what is happening in these networks and all also. And remember also, these delays are stochastic in the sense that there's a mean delay and then there's a tail. And the tail could be very long. Occasionally you may have a packet which may take a long time, okay? And why does that happen? And that is because of queuing. Because deep down at every stage, essentially what you have is it's like a server, and then the packets come in and they get processed. If you are just so unlucky that at the same time something else came in, then you're going to see a longer queuing delay. So if you measure the delay between a computer sending something over the internet to computer receiving it, or even just on your LAN, you are going to see a distribution, and the distribution occurs because of the queuing delay. And as a consequence of that, the delay which between the packet going out and the packet arriving is quite jittery. I may be sending out periodic things, but it will not be arriving at your end on a periodic manner. So now we are faced with a whole bunch of issues, right? One was this whole model of perfectly kind of a periodic arrival of tasks doesn't really hold true. We have all these kind of things, and then also this, which I already discussed, that applications give you deadline end to end. But if my processing is being done across multiple processors along the way, then I have to somehow delete that end-to-end deadline. The jitter problem in many cases can be mitigated by having buffering, but oftentimes it's a more complicated challenge. So it turns out that in these settings, where now I have multiple processors and my tasks with precedences are scattered across those multiple processors and all, things can get pretty tricky, NP complete in most cases. But kind of the basic idea is that you allocate and retry. You sort of do an assignment and check whether this results in a feasible system. If not, you kind of retry it. Okay, they're basically kind of heuristic kind of approaches. But there are a lot of weird things that happen in a distributed setting. So we'll talk about one such aspect, but just to give you an example, what a typical problem may look like is the following. I may have an application which may consist of the computation shown here on the left hand side. It has 5 tasks. We call them as P1 to P5. P1 produces data which is used by P3 and P5, and edges represent data precedent constraints. So P1 has to run before P3 and P5. So with some period, P1 is invoked, like every time some sensor data comes, P1 runs, and then P3 and P5 runs. And then I have another cluster of tasks P2 and P4, which may have a different rate. Every time input comes from P2, then when P2 finishes, P4 runs. And I may have deadline requirements on these things. Okay, so I may have these dotted lines indicate clusters. Each cluster may have a rate and then may have a deadline. And then in your system, you may be given some processing elements, PEs. So I have 3 processors, PE1, PE2, PE3. And your goal is to map these processes, P1 through P5, to the processors, PE1, PE2, and PE3, and let them run. And each processor is running our priority-based scheduler, the type which we saw sort of in previous lectures. So I may have a static priority scheduler running on P1. P1 and P2 have been mapped to that. So what will happen is whenever the input for P1 comes, let's say it's a sensor value coming from outside, P1 gets scheduled, P2 gets scheduled. Okay, and they are again done in a rate monotonic or some other static priority manner. So the challenge that comes up, so thus far it sounds simple, right? Except we have the problem of figuring out how to map things, and also I said earlier on that one of the ways we can do is we come up with a proposed mapping and then see whether it works, meets the deadlines, and if it works, doesn't work, I modify it, right? Stands to reason. The only problem in this story is that the problem of checking whether a particular mapping meets the deadlines itself is NP hard in this distributed case. And I'll show why that's the case in a moment. Remember, in the single processor case, if I give you a set of tasks along with the priority, and I ask you the question, do they meet the deadlines? What would you do? We discussed that before, right? Worst case, you apply the critical instant analysis, and you can answer that question. Here, it turns out we can't. And the reason we cannot is to look at a very simple example, and that kind of shows the difficulty we are facing out here. So what I have given is another application which have 4 processes in it. P1 feeds to Px, Px feeds to P2, and I have an independent process P3. P1, Px, and P2 share the P1, P2, and Px. They have a period of 100. Remember, they are coupled, so every time P1 runs, and Px runs, and P2 runs. They have the same period, 100, and the computation time for P1 is 10, computation time for P2 is 10, and Px can take computation time anywhere from 25 to 35. Okay, so let's say that's the situation. And P3 has a different period, 150, so P3, and it has a computation time of 30. And let's say our proposed mapping is that P1, P2, and P3 are put on processor number 1, and Px is put on processor number 2. And then finally, I only care about P3's deadline. So P3 has a deadline of 45. So now the question is this deadline met given this assignment of tasks to processors? So what it leads to is kind of an interesting situation. If Px takes time 35, then it meets the deadline. If Px takes time 25, then the deadline is missed. Okay, so already I hope some of you have noticed like what I'm saying. If Px takes more time, the system meets the deadline. If Px takes less time, then the system doesn't meet the deadline. So if what it's saying is if I make Px use a faster algorithm, or I use a faster processor speed while Px is running, then actually I'm worse off, which is totally counterintuitive, because normally one would expect if I speed something up, then things should only get better. And this is where the complexity of distributed systems come in, that you cannot simply say speeding up helps. Now let's see why that happens. And so top half shows what happens when Px takes time 35. So t equal to 0, P1 arrives. P1 runs on processing element number 1. P1 finishes at time 10. At that point in time, processor 1, Px will start running. So Px runs on processor 2, and meanwhile P3, because P2 cannot run, because P2 depends on Px, so P3 starts running. Px, remember I said takes time 25, 35, 25. 35. So Px takes time 35, P3 only takes time 30. So P3 finishes P4 at time equal to 40. This processor idles for a little bit. When Px finishes, P2 runs, finishes. Px finished in time 10 plus 35, 45. So we are done. Now let's imagine the case that Px actually takes a shorter time. So Px now takes time 25. So in this case, Px was finished at time t equal to 25. So P2 will start running now. So P3 gets preempted. And so the remaining part of P3 is going to be the after P2 is finished, and P2 now, P3 will finish at t equal to 50. So in this case, P3 finishes at 50 and therefore misses the deadline. So what happened is that if I make processing element 2 faster, or Px use a better algorithm, then P3 misses the deadline. And this is, I would assume most of you would agree that it's a little bit troubling that I make part of my system superior, but then the system fails. Okay, and that's the challenge we have in a distributed setting, that we can't simply say faster is better.
Professor?
Yeah.
The deadline is only important for P3, right?
Yeah, deadline is only important for P3. As a contrived example, but I'm just sort of to illustrate the point. So what this leads to is this is a very old theorem, but which basically says that, you know, if I have a task set which I have optimally scheduled on a multiprocessor with some priority assignment and a fixed number of processors, then a lot of things that I would do to improve the speed apparently can actually hurt me. So that includes increasing the number of processors. If I increase the number of processors in my system, maybe the system will fail. If I reduce the execution time, so make the processor faster, the system will fail. If I eliminate some precedences, some of those edges, if I remove the edges, you would normally think removing the edges is going to help me. I'm making the system task more independent. That can hurt me. So essentially, what the message that I want to take away is that in the situation when you are dealing with multiprocessors, one has to be super careful, because you can't simply just rely on saying faster is better. So there are some examples out here. I'm not going to bore you with them, but basically what we're showing is, given a precedence graph, if I this is the schedule with 3 processors. If I add up, if I add a 4th processor, the system takes more time. If I reduce the computation time, the system takes more time. If I reduce the number of edges, remove some edges, the system takes more time. So this is an example where all the things I'm doing to actually intuitively making the system better, so it should take less time to finish, it actually is ending up taking more. So not good. Yeah. So the only thing you can do out here really is you have to check. You can't simply rely on, okay, I'm going to iteratively improve. Every time you do something, you have to carefully check, analyze whether it is going to work. And it turns out even finding whether your system is meeting the deadline is actually a hard problem. So almost anything to do with multiprocessors tends to be kind of difficult and hard to do. So there's kind of not much out there in terms of canned results and all that you can use, other than one has to very carefully check for those. I'm going to skip a bunch of slides out here. So non-preemptive scheduling I'm skipping. So thus far, so another relaxation we are going to make now is, thus far we were mostly dealing with priorities which were static. I give you a set of tasks and they have static priorities assigned forever. Other than when they were sharing resources, then there was some inheritance of priority. But what if I let the priority be truly dynamic? Okay, so intuitively, you might say, if a process is close to its deadline, maybe I should give it more priority, right? Or if the processor needs more computation time relative to time remaining, maybe I should give it more priority. So in these kind of approaches, you can say, maybe I should not keep the priority static, but rather adjust the priority over time. So that's the concept of dynamic priority. And so the idea is, in dynamic priority, priorities are assigned based upon some additional consideration, and they could change at runtime. So one of the most popularly used algorithm for this thing is called EDF, earliest deadline first. It's also called least time to go. And basic idea is that the priority at any given point in time, I have a set of tasks in my system, right? They are either waiting or running or ready to run. And for each one of them, I can look at how much in the future is their deadline from now. And I can use that as a priority. So tasks whose deadlines are the closest are going to have higher priority. Tasks whose deadlines are farther away are going to have a farther away deadline. In this case, we are moving away from static priority based upon periods, as we did in rate monotonic, to one where we are looking at when the deadline is. So, and then the idea is that at any given point in time, I'm going to let the task whose priority, dynamic priority, is higher to run. There is another similar algorithm called least laxity first. Laxity refers to how much in the future my deadline is and how much computation I have to do. So let's say my deadline is a minute away and I have to do 40 seconds of computation, so my laxity is 20 seconds, right? Whereas my deadline is a minute away. So earliest deadline first will order by the deadline, whereas laxity first orders by the slack. It turns out both of them do equally well, but they actually work very nicely. So the idea, so EDF is more common and it's used quite a bit in network equipment. So preemptive earliest deadline first basically says that task whose deadline is the nearest is going to have the highest priority. So for example, let's say at some point in time, I have three tasks, T1, T2, T3. The arrival times were 0, 4, and 5, and execution time were 10, 3, and 10. And their absolute deadline are 30, 10, and 25. Okay, so in this particular case, we are going to give the highest priority to T2, just because its absolute deadline is at
I have a question about execution time. Is that parameter generally determined by the OS at runtime, or is it determined kind of like by the programmer when they create the
Okay, so I will ask you guys, who determines the execution time? So two separate questions, right? So let's say, what determines the execution time?
The program, the system, the processor?
Your algorithm and the processor. I can improve the algorithm, have a faster execution time. I can improve the processor. Who knows it?
EOS.
Really? You think so? You wrote the code, right? So OS has no way of knowing unless OS can over time learn the distribution.
Yeah, so I guess that's kind of a question. Is that something generally that the OS would keep track of
No.
as it's executing
No.
tasks now? Okay.
No. So usually you would supply it, and you supply it with some conservative assumptions. Okay.
Thank you.
So, so that's EDF, and it turns out EDF is the best scheduler in some senses that you can imagine. What among all preemptive scheduling algorithms, that is all algorithms where the OS is allowed to stop a process and restart something else, EDF, for the case where period is equal to deadline, EDF is the best. In particular, you can show that if percentage utilization of the processor is less than equal to 1, then EDF will schedule. Okay, which basically says that I look at what fraction of the CPU is needed by each task, I add them up, and if less than 100%, then EDF can do it. And if EDF cannot do it, that means that this utilization must be greater than 1, in which case nothing can do it. Right? So EDF is the best you can do. In other cases, where deadline is less than period, or deadline is not equal to period, there is no easy schedulability test, so you can't simply say this. But this is a very nice thing nevertheless, because it's basically saying if you have a choice to implement something, then just implement EDF. So why do you think, and yet EDF is not very widely implemented. Why do you think that would be the case? What about the EDF algorithm makes things harder for the OS, I guess? Let's say. Any thoughts? So the tricky thing in EDF is exactly this dynamic priority. Every time some task is moving in and out and all, the OS also has to go through and potentially adjust the priorities of the other tasks, right? So there's a lot of runtime work that the OS has to do, and in particular, it has to maintain this queue which has been sorted by the deadlines. And every time a new task arrives, I have to insert that task in the right place in the queue. So if you recall your data structures, maintaining a priority ordered queue is a lot more work, because let's say I'm maintaining a sorted queue, a new entry comes in, I have to put it. So I have to go and search where to insert that task. So if I have a lot of tasks, then maintaining this data structure itself requires some work. So EDF does come with extra requirements, expectations on the OS, which does slow things down because it has all this other stuff to do, and therefore EDF is not very commonly found in operating system. It is found in network equipment quite a bit, partly because in network equipment the speed requirements and all are just so high that people and stuff gets put into FPGAs and chips that things end up getting done out there. So EDF exists. EDF is the best in a way, in the sense that if EDF cannot do it, then nothing else can. But it does come with all these costs. Okay, I'm going to skip the EDF schedulability test, and so what we have when it comes to real-time scheduling are kind of these two broad classes of scheduling strategies. You can use things based around rate monotonic, which is static priority, and it basically says more frequent a task, higher priority it is. And then there are things around EDF, which basically says closer the deadline, higher the priority. Major advantage of fixed priority, like rate monotonic is, that is very simple to implement. Upfront, you can analyze, and it's schedulable, you can kind of do with it. The OS has to do much less stuff at runtime, and there are no priority queues being maintained at all. On the other hand, EDF has more work to do, but one thing to keep in mind is that more work, that sorted queue and all, really begin to matter if you have lots of tasks. If you only have a small number of tasks, then no big deal, you can kind of use a hash table and implement these things. Just like we had priority inversion in the static priority, there are similar issues in EDF also. What happens if the processor has more load on it? Which task will start missing its deadlines and all? So there are all those kind of issues that are present here also. So there's a whole rich body of literature around EDF as well along those lines. But barring those things, there are one big advantage of EDF is that it can utilize the processor 100%. So put another way, I can get away with a slower processor than I might with a rate monotonic system. So that can save you cost, that can save you power. So anyway, there are some other interesting properties. So EDF is pretty nice there. Okay, I'm going to skip more tasks. Okay, so yeah, let's skip the remaining slides. So to recap this scheduling part of this whole thing, so we kind of looked at timing constraints. We translated the timing constraints into deadlines and periods and things like that. And then we kind of looked at these two broad categories: static priority assignment and dynamic priority assignment. And the other dimension is preemptive versus non-preemptive. I did not go into non-preemptive much. Preemptive means that the OS is maintaining this sort of multiple processes in multiple states, and whenever it realizes there's something with a higher priority, it stops the currently running process, gives the CPU or whatever resource it is to the higher priority task. So the OS is very simple conceptually, and the whole thing boils down to is figuring out how to assign the priorities. And we saw that for static priority, rate monotonic and deadline monotonic were optimum, and for dynamic priority, EDF is optimum. EDF does what the best it can. We also saw sharing of resources between tasks. We saw resident constraints. All of these things complicate the scheduling problem. So there is, and while I've spent quite a bit of time on scheduling, trust me, I've kind of done only just scratched the surface, because there are so many different nuances. We only looked at CPUs. What if you are looking at scheduling of other type of resources? What about scheduling of communication links? There's a whole bunch of complexities that exist. So there are entire whatever people's lives have been devoted to studying scheduling problem, and to this date, like scheduling over a network. Nowadays, for example, people who are doing neural network, they're training on distributed thing. They are developing specialized scheduling algorithms and all for these kind of workloads. So there's just immense amount of work which always keeps happening in this space. We saw some scheduling algorithms which are physically motivated, or some optimization algorithms. There are also scheduling algorithms which are based around making use of analogs of real life models. So for example, in many cases, people have used economics as an inspiration. So just to give you an example, let's say I have a bunch of tasks which have to share a processor, and these are multimedia tasks, sound, video, stuff like that. And we want to make sure they share the processor fairly. So I have one task which needs, let's say, 10% of the CPU, another task which needs 20% of the CPU, another task which needs 40% of the CPU. I want to allocate them to them. But these tasks are, but I can't simply do the following, that run the processor into, like, divide the time slots and say, now this task done, because the task may not be ready to run. So one example that Linux uses, or some versions of Linux uses, something called lottery scheduling. And the idea in lottery scheduling is the following. So much like real life lotteries, we buy tickets. Your chance of winning the lottery depends upon how many tickets you have, as a fraction of the overall number of tickets. So in lottery scheduling, the processes are given lottery tickets, and every time step they bid. They basically, depending upon how many tickets they have, the operating system is going to select them with that. So lotteries have been an inspiration. Another economic system which gets used quite a bit for resource allocation is this whole concept of bidding for an object. So auctions where sort of there is an object and everyone kind of bids for it, and kind of the idea is that if you think you will benefit from having that resource, you are going to bid higher. So again, in many systems, network systems and CPU systems, they run an auction, and the idea is that if I need one more unit of time, and it's going to improve my performance a lot, then I'm going to bid more for it. Okay, so auctions. So there's a body of work out there which kind of has looked at economic systems. So there are many other examples which obviously I didn't get into. Another one area where people have spent a lot of time is the non-preemptive case. So non-preemptive, if you recall, is the notion that once the task starts running, it cannot be bumped off until it finishes. So non-preemptive introduces additional complexities. I have to be very careful when handing over the task, handing the CPU to a task, because then it will have the CPU for a while. In a preemptive system, if I made a mistake, I can bump it off. The OS can bump it off. But in a non-preemptive, I can't. If I start sending a long network packet, I have to wait until its transmission is finished. So that leads to another concept which we didn't touch upon. It's called work conserving scheduling. So thus far, again in our systems, we kind of assumed if I have a task which is ready to run and the CPU is free, the task will run. Can you think of an example where there is a task ready to run, the CPU is free, but you can choose not to run it still? Why would you do that? So think about it. There's a task in the system, there's a task which is ready to run, CPU is free, and I'm making the case that you might be better off not running it.
Maybe.
Can you speak louder, please?
If you try to write to some device volatility solution.
No, it's ready to run. So everything is available. The task can run. If I let it run, it will run happily. But I'm claiming that you may be better off not running it.
Maybe the CPU was reserved for another task.
No, I mean, you're deciding the scheduling strategy, right? I mean, so there's no such thing as reserved and all. It's ready to run. No reservation. Okay, and I'm still saying that your better strategy may be not to run it.
If you're about to get a different task in that has
Exactly.
short deadline.
If you have learned about the patterns of arriving task and you know a short while later something super critical, super important is going to arrive, and it's a non-preemptive system, so if I give the CPU to this task, I'm kind of stuck. So I may just wait for it. Okay, so that is called non-work conserving schedulers. That is, I may deliberately choose to keep a resource free, and that may be my optimum strategy. So I guess the thing I'm just pointing out that all these other cases and all that occur, and kind of like how do you make use of it? Nowadays, a lot of people are looking at neural networks and all to make these scheduling predictions and all. So it's a never-ending area, as you saw from some of the citations I had. I mean, the scheduling problem goes back decades. People have always worried about scheduling ever since computer science has existed. There's an area of inquiry called operations research. Those guys spend time on scheduling, mathematicians do, electrical engineers do, and we keep facing these problems with different twists and all the time.
So related to the previous question I asked about how do you know the execution time for what you just described?
Mm-hmm.
I guess the OS to know future things that are coming in, that would have to be complex, more advanced than a typical OS that we deal with. Is that right?
Yeah. So no. So your question was right on, and I think I kind of keeping things deliberately super simple. So generally, operating systems that we encounter don't do a whole lot of learning about the task.
And it wouldn't be able to do what you just described of
Right.
knowing, let me not
Right.
do this task.
But there are plenty of examples where operating systems begin to profile the tasks. Okay, they begin to learn about what is the period with which this task comes, how much time it takes, and all, and then makes use of it. Particularly operating systems which are doing aggressive power management have begun to do that. They begin to predict when the task will arrive, how long it will run, and then they make use of all of that for their decision making. So I guess the deeper answer to your question is yes, operating systems can be super sophisticated nowadays. Yeah. So anyway, let's see. So how are we doing on time? So we are 7:36. So I'm going to start on a different topic entirely now. So thus far, we spent time on, again, given timing constraints and stuff like that, how we kind of meet it. But one question we kind of assumed was that somehow our systems knew the time and knew the time accurately, and so all of that was taken for granted. So the next set of lectures I'm going to go after that, that how is that time known, and we'll also look at the broader problem, which is computers of this type, embedded computers, need to be aware of the physical context. Time is one of the physical context, but there are other things like location and power and all which fall into the same category. So I want to start by kind of some discussion on how do computing systems know time. Clocks obviously are a part of it. So, and what kind of challenges arrive, what kind of imperfections occur in these things, and what their manifestation, what their implications are. So we're going to spend some time on that. Okay, so of course, the desire to know time or the need to know time has been around for a long while, and I guess the first big impetus towards measuring time accurately occurred a few hundred years ago, and it was driven by when Europeans started navigating the world, and they needed to navigate accurately, right? I mean, if you could navigate with land always in sight, it's much easier, but if you have to navigate in the open seas with basically water and stars and nothing else, no landmarks, then things are a lot trickier. So it turns out that latitude can be measured by a sextant, basically measuring the angle of the stars or angle of the sun. Like you can basically measure during daytime with the sun, at nighttime with the star, kind of what. So how far north or south of the equator you are, that is easy to measure. Longitude is difficult. So to measure longitude, you also need accurate time. And the reason you need that is because if you think about it, what happens is as the Earth rotates, then the stars relative to you are shifting because of the rotation speed of the Earth. So by looking at when the star or when a particular celestial object, when a star is above you and when it was above some other known place, and by comparing the difference, you can work it out. So imagine the following: you're leaving your home base, you measure when sun was right overhead, measure it on your clock, and then wherever you are in the middle of the sea, you measure when sun is overhead according to that same clock, same accurate clock. Then the gap between it, if according to your clock at time 12 noon the sun was overhead at your home base, and it is 10 seconds past 12 noon when it is overhead wherever you are, then that 10 second is telling you about the longitude. Okay, and because of that rotation of the Earth. So that's the concept of local time. So longitude, one of the ways you could do it is through accurate time. There could be others, and there are others, but they were equally problematic. So back in then 15th century, major prize, the X prize of the day, if you may, was set up to, for someone who would create 18th century, 1740, a $2 million prize in today's terms for creating something which was accurate enough to keep time, so that you could measure the longitude of the ship accurately enough so that the ship could be localized within a certain distance. Okay, essentially a very precise clock. And moreover, this had to be a clock. Remember, there's no GPS, there's no electronic clock and all. So the mechanical clocks kept on a jostling ship and all. So they also had to be immune to the storms that the ship is facing and stuff like that and all. So in this case, it was simply to compute the location. If you guys, I don't know, have any of you ever been to the museum in London, which is the Greenwich Museum? Have you been? Yeah. Okay. It's a fascinating place because you will find all that history of clocks and time there. I mean, including the original pieces and all kept. It's actually, and that's where the prime meridian is. So you can stand with your 2 feet across 0 degree, I guess both in western and eastern hemisphere at the same time. But anyway, so that's it. Starting with that, there obviously we have come long ways, and of course starting from long before when sundials and stuff like that. So nowadays, of course, you have atomic clocks, which are the super precise, very stable clocks. There are even chip scale atomic clocks. Our electronic devices tend to use, actually, that's the next slide. Our electronic devices use quartz crystals, and there are a whole bunch of other technologies that have come to bear. There you can buy reasonably very precise clocks now for $1,000 or so for scientific uses and all. If you are richer, you can even buy an atomic clock. There are chip scale atomic clocks you can buy now for $1,500 for the chip and some more stuff. So there's pretty precise stuff which one can get. Even if you don't have a precise clock yourself, you can use communication to a remote precise clock and then synchronize your clock very precisely, which is how we derive very accurate times from the GPS satellites. So you can transfer time between computers with using certain protocols. So we'll talk about now there. So you can, so essentially, I guess what I'm trying to say is you can either have a local very precise clock, or you can design a protocol and a network to access a remote clock and then set your clock very precisely. And long story short, now we can measure things very short time intervals. We can keep frequency stable for a long time. We can keep clocks synchronized across the globe very precisely. So a lot of these things have become possible, and there are all the things that follow from it. So the original intent of that prize by the British government was very precise locationing. And indeed, when we think of GPS, we always think of positioning, but GPS would not be possible without timing. So it's really actually the wonders of timing that make GPS possible. But there are a whole bunch of other things where computing systems benefit from precise timing. Examples, anyone? In what ways precise timings help computers? Come on, name one at least, guys. If we were to replace your computer's notion of time with some absolutely rotten, inaccurate notion of time, what all will break?
Helps with interval scheduling.
Huh?
You have helps with interval scheduling. You have the multiple processes when you do multi-threading.
Okay, so it will, but what are the implications of that? Okay, so it will make my scheduling inaccurate, but what implications would you see?
Communication with other devices.
Say it again.
Communication with other devices.
Okay, so communication with other devices will be impacted, right? I mean, oftentimes these communications are synchronized somehow, right? But don't go too deep. Just think in terms of what all you use where notions of time matter.
Two-factor authentication.
Okay, great example. Yeah. So how many of you have used? Well, I suspect all of you use that Duo mobile stuff that UCLA makes us use, right? So when you open it up, it has this rotating series of number comes and it keeps changing. And it is dependent upon time synchronization because that is valid for a certain time and it takes into account some slippage and all, but if it is too far off, then it won't work. Okay, great example. So security. a lot of security protocols need to use time. Okay, what else?
Interrupt.
Huh?
Interrupt.
What about interrupt?
Inner interrupt.
Huh?
Interrupt based on timing.
Yeah, but what implication would it have?
Some manufacturing is time sensitive. For example, the step one have to be controlled within 1 minute or 2 minutes. It require a precise time.
Okay.
When the time up, have to switch to step two. Otherwise, the product will be failed.
Okay. Okay. So am I the only one who uses calendars? Sounds like none of you mentioned calendars. Don't you use calendars with reminders and all, right? They will go awry if that notion of time was messed up, right? You'll be always be early to the class, for example, if clocks are faster. Okay, what else? What else? How do you think sensing would be impacted? Sensors, how would they be impacted if our measurement of time was incorrect? Or will they be impacted?
Yes, you wouldn't be able to correlate the output from the sensor with like other data. Right?
Okay, so I may have two cameras and says I saw a person in whatever black shirt, and the other camera says a second later I saw the person in black shirt, and so we know the person moved from camera 1 to camera 2. But if they were not synchronized, we would say it's going in the other direction, right? So absolutely, being able to correlate information across distributed entities becomes a problem. Okay, what else? If I were to tell you Wall Street is super interested in precise timing, why do you think that might be? Or actually governments are forcing Wall Street computers to maintain very precise clocks. Why do you think that might be?
For record keeping,
Yeah, what kind of record keeping?
trade.
Yeah, but that could okay. They want them to be in even to nanosecond level. Why do you think that might be? Nanosecond, microseconds. Why do you think they would want Wall Street computers to be that accurate?
Because the market at the certain time the market will open. Yeah, and I think maybe the information is most important. If the time is not accurate, somebody will maybe know the information earlier than
Yeah,
others.
so you're right. So have you guys heard of algorithmic trading, or even things like, right? I mean, if you place the order, I'm the company, you're placing the sell order, and I am able to mess with it, and I basically am able to get my order ahead of you in the queue, and I have seen your order, and so I can make money, right? I mean, so the governments are want to be able to timestamp every action the Wall Street computers across the industry are taking, so that they can identify rogue trades and stuff like that. So there's a requirement, very stringent requirement of timing. So when we talk about this, I think we are out of time now, but precise timing requirements are just all over, really, and we're going to spend some time kind of looking at that. Okay, so see you guys on Monday. And I'm going to be there in my office for the next hour or so.